We're looking at the paper Team of Thought's Efficient Test Time Scaling of Agentic Systems through Orchestrated Tool Calling.
Yeah, by Wang Zhang and the teams at Imperial College London and Microsoft Research.
The core problem they tackle is that existing multi-agent systems generally rely on static homogeneous models.
Right, the same model playing different roles.
Which limits the diversity of reasoning and is incredibly token inefficient.
So their solution is a novel framework called Team of Thoughts.
Treating different LLMs not as monolithic reasoners, but as specialized tools.
It uses an orchestrator to dynamically select the best tool agents based on the specific tasks.
And there are two key innovations here. First, orchestrator calibration.
Finding the best model to coordinate the team, which actually isn't always the largest model.
And second, self-assessment.
Tool agents profile their own proficiency on validation sets so they can tell the orchestrator exactly what they are good at.
The key result from all this is that the system achieves 96.67% accuracy on the AIME24 math benchmark.
And 72.53% on LiveCodeBench.
Significantly outperforming homogeneous baselines like Agentverse.
While actually being more cost efficient.
Okay, so that is the quick rundown of the paper. Welcome to AI Paper Podcasts.
Glad to be here for this one.
We are doing an in-depth analysis of this today because, 96% on AIME deserves a serious explanation.
It really does. It's a massive jump.
Let's start with the context here because everyone is talking about test time scaling right now.
Oh yeah, TTS is definitely the flavor of the month.
And for good reason, right? We are seeing diminishing returns on pre-training scaling.
Exactly. You can't just keep throwing more GPUs at the training phase forever.
At some point, you hit a wall.
You do. So the industry is pivoting to test time scaling, basically investing compute during inference.
Right. Asking the model to think longer using chain of thought or tree of thoughts before it spits out an answer.
But the authors of this paper argued that the current approach to multi-agent systems is hitting its own wall.
A mathematical wall. They call it the homogeneity problem.
Let's break that down because it's a probabilistic view. Think about a single model, say GPT-4.
Okay.
It has a specific set of parameters, right? We represent that as theta.
Theta.
Those parameters define a fixed prior distribution over the possible solutions.
So it has a very specific worldview, a specific bias.
Exactly. Even if you use temperature sampling to get slightly different outputs.
Or prompt it to be different personas.
Like, you are a skeptic, you are an optimist.
Right.
It is still exploring the solution space from that exact same initial anchor point.
It's kind of like asking one person to debate themselves.
Yeah, they might come up with a few counter-arguments, but they can't genuinely surprise themselves with a completely new perspective that they don't possess.
And this applies to multi-agent systems, too.
Yeah.
Because usually people think, oh, I'll just spin up 5 agents and have them vote on the answer.
That is the trap. If those 5 agents are all instances of the same model, you are just scaling the echo chamber.
You just get 5 GPT-4s agreeing with each other.
You might get a consensus, but it's often a false consensus because they all share the same blind spots.
So if the base model is bad at, say, non-Euclidean geometry,
5 copies of it will just confidently agree on the wrong answer.
So the solution isn't just quantity of agents.
No, it's diversity, heterogeneity.
You need models that have completely different post-training backgrounds.
Different training data, different architectures, different priors.
That is the only way to truly cover the solution space.
Which brings us to the actual architecture they propose. Team of thoughts or 2T.
Right. They aren't just throwing random models into a chat room and hoping for the best.
No, it's a very rigid, efficient structure. They reconceptualize LLMs not as monolithic reasoners, but as specialized tools that you call via an API.
So visualize this. We have an orchestrator sitting at the top.
And below it is a library of incredibly diverse models.
Claude GPT, Gemini, DeepSeek, Qwen.
All of them.
I want to drill down on this orchestrator setup phase because this was the first thing in the paper that really caught me off guard.
The calibration part.
Yeah, I just assumed the orchestrator would be the biggest, smartest model you can get your hands on. You put the genius in charge, right?
You would think so. Logic dictates the smartest model makes the best decisions.
But the researchers actually ran a calibration phase to test that assumption.
They evaluated different models specifically on their ability to coordinate tools and aggregate responses under a budget.
And the results were completely counterintuitive.
Very much so. For mathematical reasoning on AIME DeepSeek v3.2 was the best orchestrator.
Okay, but for coding tasks on benchmarks like MBPP, plus the winner was GPT-5 Mini.
The mini model.
Why would a smaller distilled model be a better boss than the flagship model?
It really forces us to rethink what intelligence actually means in a system context.
How so?
Well, the flagship models, the massive ones, they have very strong priors. They are opinionated.
Right.
When they see a user query, they might just try to solve it themselves immediately.
Instead of delegating.
Exactly. Or they might hallucinate details because they are so generative by nature.
So they're basically bad listeners.
In a way, yeah. But a model like GPT-5 Mini, which is likely optimized heavily for instruction following and efficiency.
It acts more like a good project manager.
It doesn't try to be the hero. It looks at the instructions, which are, find the best tool for this job, and it just executes that logic strictly.
It adheres to the system prompt better than a model that thinks it knows everything.
Managerial capability is totally distinct from raw reasoning capability.
That is fascinating. You don't want your project manager writing the kernel code.
No, you want them coordinating the specialists who write the kernel code.
Okay, so we have our manager, let's say it's GPT-5 Mini for a coding task. A complex query comes in. How does it actually know which tool to pick?
Usually developers just hard code this, right? If math, use calculator. If writing, use Claude.
But hard coding is brittle.
Very brittle. And it assumes the developer knows the model's exact strengths perfectly, which they don't.
So this paper flips that. They use tool agent self-assessment.
This is a rigorous pre-computation phase.
It felt almost human to me when reading it. The agents write their own performance reviews.
Effectively, yes, but it's not a subjective essay. Before the system ever goes live, every single tool agent runs through a huge validation set of problems.
And they generate a model persona profile based on their performance.
And this persona isn't just a generic, I am good at math.
No, the prompt templates in the appendix show they require the agent to list core competencies, but more importantly, blind spots.
Blind spots are crucial.
Give an example of what an LLM blind spot looks like in one of these profiles.
So based on the validation, an agent might literally output thosod. I am proficient in generating Python scripts for data visualization, but I consistently fail when asked to use the Asensio library for concurrency.
Wow, that is incredibly specific.
Or for math, it might say, I can handle complex calculus, but I struggle with combinatorial problems involving negative integers.
And that specificity turns into routing data.
Exactly. The orchestrator ingests all these personas.
So when a new query comes in about asynchronous Python, it doesn't have to guess.
It looks at the profiles and says, okay, Agent A admits they messed this up. Agent B says they are strong here. I am calling Agent B.
It decouples the profiling from the orchestrator's own biases.
That is a massive point. They actually ran an ablation study on this exact mechanism.
We compared self-assessment against orchestrator assessment right.
Where the orchestrator tries to guess who is good.
And self-assessment won out.
Significantly. For math, self-assessment led to that 93 to 96% accuracy range. Orchestrator assessment dragged it down to around 90%.
Why is the boss so bad at judging the talent of the team?
It's a cognitive ceiling issue. If the orchestrator isn't an expert in advanced number theory, it simply can't accurately judge whether a subordinate is a genius at number theory.
It might rate a brilliant but complex answer as confusing.
Right. But if the subordinate grades themselves against a ground truth validation set, the signal is mathematically pure.
It's just, I got these right and I got these wrong.
The orchestrator respects that hard data, not its own intuition.
You want the scorecard, not the vibe check. So let's walk through the actual Inference workflow. I am a user and I drop a really nasty math problem into the chat. What happens step by step?
Step 1, the orchestrator receives the query. It analyzes the complexity in the domain.
Step 2.
It consults those model personas we talked about. It immediately filters out anyone who isn't relevant. If it's math, the coding agents are ignored.
Which saves money right off the bat.
Yes. Then it selects the best tools. Maybe it picks DeepSeek V3 and GPT-4o because their profiles show they have complementary strengths for this specific math subdomain.
Step 3 is the actual tool calling.
It uses native tool calling APIs to invoke them simultaneously.
Parallel execution. That's a big deal for speed.
Huge. In a traditional chain of thought, you wait for step 1 to finish, then step 2. Here, the orchestrator fires the pistol and everyone runs at once.
Which massively reduces latency compared to sequential reasoning chains.
Absolutely. Then the agents return their reasoning phrases.
And the orchestrator does the aggregation step.
It synthesizes the answers. It resolves any conflicts based on the confidence scores from the personas and outputs the final result to you.
They also mentioned something called strategic token allocation. It sounded like a corporate budget meeting.
It is a budget meeting, but it happens in milliseconds.
Because the system operates under a global token cap, right?
Right. And because the orchestrator knows the exact proficiency of the agents, it doesn't have to give everyone the exact same microphone time.
So it can just tell the intern to keep it brief.
Literally, yes. It might say, Agent C, you are just a backup here. Give me a 50-token sanity check.
While Agent A gets the spotlight.
Agent A, you are the specialist. Take 2,000 tokens and show your work step by step.
It's dynamically allocating compute resources to where they will have the absolute highest impact on accuracy.
That brings us perfectly back to the results.
We threw that 96.67% number out at the start. I want to contextualize how absurdly high that is for the AIME 2024 benchmark.
It's startling for anyone who works with these benchmarks.
Give us a baseline.
Claude 3.5 Sonnet, which is widely considered one of the best reasoning models out there, scores somewhere in the mid-80s on a good day.
GPT-4 is pretty similar, right?
Yeah, around there.
So a single top-tier model caps out around 86%.
Right. And here is the real kicker. Agentverse, which is a very popular multi-agent framework where identical models debate each other.
What did they score?
They scored around 80%.
Wait, so the multi-agent team actually did worse than the single model?
In the Agentverse setup, yes. That is the too many cooks problem, or really the homogeneity problem in action.
They just talk each other into bad ideas.
Because they share the same primate, they reinforce their own hallucinations.
The team of thoughts hit 96.67%. That is near perfect.
It suggests that the error surfaces of these different models, DeepSeek, GPT, Claude, are almost completely disjoint.
Meaning the things DeepSeek gets wrong, Claude happens to get right.
And vice versa. When you have a smart orchestrator that knows exactly who to trust for which specific subproblem, you can effectively filter out almost all the noise.
What about the coding side? LiveCodeBench.
Team of thoughts hit 72.53%.
And Agentverse.
Down at 65.93%. So the gap holds up consistently across domains.
But for the engineers listening, you were saying the accuracy chart isn't even the most exciting part of the paper.
No, it's the cost chart.
A Pareto-efficient frontier.
Exactly. In AI engineering, there is a universal rule of thumb. Accuracy costs money.
Right. If you want that last 1% of reliability, you usually have to double your inference cost.
Run more samples, do heavy verification loops.
The team of thoughts broke that rule.
They smashed it. They achieved higher accuracy than Agentverse while actually using fewer total tokens.
How is that even mathematically possible if you were calling multiple models per query?
Because they aren't looping. Think about how a consensus system works. Generate answer, critique answer, refine answer, vote, tiebreak, refine again.
That sounds exhausting.
It is. For hard math problems, Agentverse might loop 10 times. For code, the paper notes it can take up to 1,000 retries to get runnable code in some agentic loops.
1,000 retries. That is just burning money on API calls.
It's the brute force approach. Team of thoughts is the sniper approach.
Because of that pre-computed self-assessment.
The orchestrator selects the exact right expert immediately. It gets the right answer on the first or second try.
You completely cut out the massive debate loop.
You don't need to ask for 5 rounds of critique if you know you hired the model who historically never misses on this specific topic.
So it's more efficient simply because it is incredibly decisive.
Correct. It shifts the compute spend from iterative searching to intelligent routing.
I want to touch on the implementation details for a minute because this all sounds amazing in a white paper. But how practical is it for someone to actually build?
It's surprisingly practical. The self-assessment phase is just a one-time cost.
You just run it once when you onboard a new model to your library.
Exactly. You run the validation set, generate the JSON profile, and store it. The actual runtime inference is just standard API calls.
And they used a mix of models for this, right? This wasn't just an all-proprietary OpenAI setup.
This is a huge deal for the open source community. They mixed proprietary models like GPT-5 Mini and Claude with open weights models like DeepSeek and Qwen.
That feels like the true future of enterprise AI to me.
It absolutely is. We are rapidly moving away from the one model to rule them all paradigm.
We are seeing the commoditization of intelligence into functional components.
If you are building an app, you do not need to be locked into just the Anthropic ecosystem or just the OpenAI ecosystem.
You can basically play Moneyball with your AI agents.
That is the perfect analogy. You can have a cheap, fast, local model like Qwen handling 80% of your user traffic.
The easy stuff.
Yeah, and then you configure the orchestrator to only call the expensive heavy hitter like Claude Opus when the query hits a specific complexity threshold that you defined in the persona.
It is a true best-of-breed architecture.
And it makes your application so robust if a new state-of-the-art model comes out next week, say Llama 4.
You don't have to rebuild your entire system from scratch.
You just run your validation set on Llama 4, generate its persona, plug it into the orchestrator, and boom! It starts getting routed tasks immediately where it excels.
It effectively abstracts the intelligence layer away. You stop caring about the brand name of the model and start caring exclusively about its proficiency profile.
That is the big shift. We are moving from model-centric design to system-centric design.
I do wonder about the prompt engineering required to make this orchestrator behave, though. It seems like a complex routing model could easily go off the rails.
It requires extreme discipline. The paper actually includes the prompt templates in Appendix C, and I highly encourage everyone listening to look at them.
Are they super complex?
They are very structured. They force the orchestrator to perform a per-problem analysis.
Meaning what exactly?
It has to classify the problem taxonomy, issue a strict pass or fail prediction for the available agents, and then explicitly justify the tool selection before it is allowed to make the API call.
So it's not just pick the best one. It's show your work logically on exactly why you picked the best one.
Yes. It constrains the action space to prevent the orchestrator from getting lazy or just defaulting to a favorite flagship model.
So zooming out here, for the last 2 years, we have been trained to look for scaling laws.
Right, bigger parameters, more data, bigger GPU clusters.
But this paper is proposing a fundamentally different kind of scaling law.
It's the inference scaling law. We used to think inference scaling just meant sample 100 times and take the majority vote.
But this paper proves that inference scaling can mean route intelligently exactly once.
It proves that a coordinated team of diverse, specialized experts, even if some of them are smaller models, consistently beats a group of massive clones.
Every single time. And it's not just about raw accuracy. It's about redefining reliability.
Which leads into an interesting philosophical point.
Yeah, I had a thought while reading their conclusion. We talk a lot about AGI, artificial general intelligence.
We assume the path to AGI is making a singular model that knows literally everything.
The omniscient God model. But this paper achieved near-perfect benchmark results, not by making the underlying model smarter, but by making them more honest.
That is the unlock of the self-assessment phase.
It really makes you wonder, if models can accurately self-assess their own blind spots, are we approaching a point where the most critical part of an AI system isn't the raw intelligence itself, but the self-awareness of its own limitations?
That is a profound question. In human engineering teams, the most valuable member isn't always the smartest person in the room.
It's the person who knows exactly what they do not know and knows exactly who to ask.
Reliability comes from humility.
It does. Perhaps the path to truly reliable AI isn't just building a bigger brain, but a more honest one.
If we can engineer systems that know exactly when to yield the floor, we solve the hallucination problem not by fixing the hallucination itself, but by routing around it entirely.
That is a very optimistic take on the future of these systems. It's not about one superbrain. It's about a society of minds working in concert.
And the Team of Thoughts paper provides the literal blueprint for building that society.
Well, on that thought, we're going to wrap up this deep dive. If you are building AI agents and want to build your own team of honest specialists, definitely check the links for the paper.
Specifically, look at Appendix C for those orchestrator prompts.
This has been AI Paper Podcasts.
Thanks for listening, and we'll catch you next time.